Let's start with this specific problem today, where we have got a uniform hemisphere. Now when I say hemisphere, I mean that it is completely solid inside. So here is a hemisphere which has got a total mass m, which has got a radius r, and we have to find out where the center of mass of this hemisphere is. The center of this hemisphere is at some point O here. So you've got a point O here, and we want to find out where would be the center of mass relative to this point O. Now we know that there is one axis of symmetry in this problem, and that is this y-axis here. So the center of mass must lie on the y-axis. So that's one thing. Second, I know that I can break this entire hemisphere into hemispherical shells. There will be infinite hemispherical shells into which I can break this whole thing up to whole thing into, and each of those hemispherical shells will have the center of mass somewhere, and I know where is that center of mass. We have done that in the previous class. So I believe that was r/2 for a hemispherical shell. So then the job becomes very simple. You break this entire hemisphere into hemispherical shells. Take some arbitrary hemispherical shell like what I'm going to take now. So let me copy this figure, paste it here, and take a hemispherical shell. Let us say this big, and increment the size by a small amount. Let us say make it that big and fit it here. Yeah. So what I've got is a very thin hemispherical shell of r radius. Let us say there is a small r radius here. So this entire thing is small r, and let us say I increment the radius by a very small amount, dr, and what I will have is a red shaded part that is an incredibly thin hemispherical shell. Now I need to find out the mass of this shell. The mass of this shell can be very easily found if I just use the volume mass density here. So its small volume is going to be 4 pi r square dr, but you see that that expression is for the volume of a spherical shell, not that of a hemispherical shell. So I will have to divide this by 2. So this is 2 pi r square dr. That's the volume of this red shaded portion, and then its mass becomes 2 pi r square dr times rho, where rho is the volume mass density. In this case we can find out the value of rho because we know the mass of the total hemisphere and the radius of this hemisphere. So rho will be, where rho is equal to big M by 2 by 3 pi r cube. We don't have to use this value. In fact, I'm just showing you how to find out rho so that you should be able to find it out, but then we don't have to use it here. The mass of this red shell is now known. And where is the center of mass of this red shell? The center of mass of the red shell is at a point that is small r/2 away from the center, because that is what we have seen for a shell. For a thin uniform shell, the center of mass is halfway through the radius. So now what I can do is this entire red shell, I can replace it as a single point mass placed at this point, small r/2 away from this point O. So I can say that now I have got this much mass, 2 pi r square dr into rho, at a point which is r/2 away from the origin along the y-axis, and so y center of mass is, so now for this hemispherical shell, y center of mass is going to be small r/2, and I know now that for this entire figure I can find out the center of mass as y center of mass for the complete hemisphere is equal to integral of r by 2 times dm, and this integral has to be performed for all the shells starting from a 0 shell size to the largest shell size, which is big R, and divided by integral of dm. And what will the numerator become then? So therefore the numerator will be, so therefore numerator is integral of r by 2 times dm is 2 pi r square dr into rho, 2 pi r square dr into rho, and this integral has to go from limits 0 to capital R, and I think we can do everything in one step. So 2 and 2 cancels out, 2 and 2 here will go off, and then you will have pi and rho going out, and you will have small r cube dr, so that will give you small r power 4 by 4. When you apply limits, it will be big R power 4 by 4. That is what you will get for the numerator. And what do we get for the denominator? So the denominator is integral of the dm term. Dm term is here 2 pi r square dr into rho, 2 pi r square dr into rho, and this integral has to be done from again 0 to capital R. So you again do the same things. You take 2 outside, pi outside, rho outside. So you have got a 2 pi rho, and then you have got a r square dr, which will give you r cube by 3, and using the limits will give you big R cube by 3. So therefore now y center of mass for the total hemisphere is pi rho r power 4 by 4 divided by 2 pi rho r cube divided by 3, and some terms obviously will go off like pi and rho, and r cube and r power 4 will go off, and there will only be a r left over in the numerator here, and you will have 3r by 8. So this is the center of mass of a uniform solid hemisphere. So when you look at that 3r by 8 term, you will see that it is less than halfway through the radius. So this is just to give you an idea of where the center of mass lies. So if the r by 2 point is shown as that black cross, which is the radius divided by 2, then slightly below that will be the center of mass here. This height will be 3r by 8, and that's it.